Okay, and we're very happy to have Leonid Rybnikov from Higher School of Economics, and he'll tell us about Bethe, subalgebras, and Yangians, and absolutely wonderful compactification. And so it's an honest whiteboard talk, but Leonid promised to write in capital letters. So yeah, okay, please.
Okay. Thank you very much for introducing me and for inviting me to give a talk at the seminar. So I will speak about my joint paper with Alexei Ilyin. About Bethe subalgebras in Yangian and the Concini Procesi wonderful compactification of the Lie group. And let me start from some simple example to demonstrate what problem I will be addressing. So consider the Yangian of GL2. This is an algebra generated by infinitely many generators T, I, J, R, where I, J are 1 or 2, and R are all natural numbers. Up to relations. Tij r plus 1 tkl s minus tij r tkl s plus 1 is going to be T K J R T I L S minus T K J S T I L R. These are the defining relations, and they define some Hopf algebra deformation of the universal enveloping of the current algebra GL2 of T. Where Tij R is the generator deforming the usual one E I J times e to the power R, R plus R minus 1. Sorry. Okay. Okay. So these defining relations can be packed in the following way. So let me consider the generating function Tij of u being the sum delta ij plus sum r from 1 to the infinity Tij r u to the power minus r. And let me consider the 2 by 2 matrix whose matrix elements are these power series Tij of U. So T of U is a matrix T11 of U, T12 of U, T21, 2. Then the defining relations can be written in the following form. R of U minus V, T1 of U, T2 of V equals T2 V, T1 of U, R U minus V, where, let me explain what is written here. On both sides of these equations are elements of the tensor product of 2 by 2 matrices times 2 by 2 matrices times the Yangian, depending on two formal parameters U and V, with T1 being so T1 being just T of U inside the tensor product of the first copy of matrices, tensor Yangian. T2 of V is embedded in the tensor product of the second copy of matrices times the Yangian, and the matrix R is just an element from matrix times matrices, R of U minus V is just a matrix and is given by the formula U minus V is just 1 minus permutation matrix over U minus V, where P is matrices, tensor matrices. Okay. So now I would be interested in some commutative subalgebras. In the Yangian, I will describe a family of commutative subalgebras depending on an element from GL2. V of C in the Yangian Q of GL2, where C is a group element from GL2. So let me define them. And, so these subalgebras are going to be maximal commutative subalgebras of maximal possible size. So the definition so first I want a maximal commutative subalgebra in the Yangian. And of course, if I want something maximal commutative, it has to contain the center of the Yangian. So maybe before definition, let me define the center of the Yangian. This center is known to be generated by a quantum determinant. Quantum determinant, which is the power series defined as trace, one half of trace of T1 of U times T2 of U minus 1 minus vice versa. T2 U T2 of U T1 of U minus 1 so what is written here is an element from matrices, tensor matrices, tensor Yangian of GL2, and I am taking the trace over this. Okay. So this is again a power series in U to the power minus 1. So it is 1 plus sum dr U to minus r from 1 to n. And all these guys are known to be algebraically independent generators of the center of the Yangian. For example, the first of them, D1, is just T11 first plus T22 first. The second one is some quadratic expression and so on. Okay. So this is the center, and of course the center belongs to any maximal commutative subalgebra in the end. Next, let me define something additional. Proposition. The following elements, let me denote them tau of U C, just trace C times T of U, where C is some fixed element from GL2. Pairwise commute for all possible U. Have T of UC, T of VC, is tau of VC, tau of UC. This means that if I write the Fourier coefficients of this series, tau of UC is trace C plus sum of some elements from 1 to infinity, tau of C R. times u to the power minus r. All these Fourier coefficients pairwise commute. So it is equivalently we have this property. All tau of c are pairwise commute. I'll prove. Let me prove this because it is really easy. So I want to show that the product in one order equals the product in other order. That is, I have to show that trace C T of U C1 T1 of U times C2 T2 of V trace over C2 times C2. This is the left hand side equals the trace of C2 T2 of V times C1 T1 of U. This is the right hand side. So I have to show this. Want to show this. Note that nothing changes if I insert R of U minus V here and R of U minus V inverse here. Nothing changed, but after that I can use the defining relation of the Yangian. After that I use the following. So I use that the R matrix is invariant with respect to simultaneous action of GL2 on both tensor copies. So R commutes with C1 times C2. This guy commutes. So
by tangent in the tensor product?
Sorry?
But C1, C2 should be C1 tensor C2, right?
Yeah. So it is C tensor C.
Mm-hmm.
And it commutes with both one and the permutation matrix.
And C technical does not have to be invertible, right? So it's not in GL2 but rather in matrix.
Yeah. So the standard definition, the general definition requires C to be a group element, but in this particular case where our group is GL, we can assume that C is just a matrix. Right. Okay, so so the R matrix commutes with C tensor C, and putting it here changed nothing. So we can apply the defining relation and see that the conjugation of the thing by the R matrix is this. So it is really easy. Now, the goal is to describe all possible commutative subalgebras arising as the limit of subalgebras from this family. Describe commutative of subalgebras B of C, where C goes to some limit. I mean that the parameter space of this family of subalgebras, so as defined is GL2, and this is a non-compact space. So I can take some limits. I can take some, for example, some sequences of C's and watch what is the limit of subalgebras corresponding to the elements from such sequence. And I can ask what I can get, and what is actually the true parameter space for commutative subalgebras in the Yangian of GL2. So, for example, as Sasha already mentioned, I can take the limit when C becomes non-invertible. So I get some new commutative subalgebras. And one more remark: this subalgebra B of C, so subalgebra. Sorry, let me. Maybe I didn't define this. So B of C is the commutative subalgebra generated by the coefficients of quantum determinant and by Fourier coefficients of tau. It depends on C. So let me remark that this commutative subalgebra does not actually depend on C. So I mean that doesn't change when we multiply C by a constant. So B of C equals P of lambda C for any non-zero lambda C star.
Leon, and it shouldn't be immediately obvious that BFC is maximal commutative, right? Or it should be.
It is not immediately obvious, of course. Right. So right. In fact, it is. It is almost obvious for generic C, because being maximal commutative is an open condition on C. The risky open condition. So we have just to find some particular point and properly limit point such that the corresponding subalgebra is maximal commutative for some obvious reason. And such particular point is the following. So let's see, be a degenerate matrix 1, 0, 0, 0. Then the corresponding subalgebra is generated by Q det and T1, 1. Right? And moreover, it's so Yangian GL2, and if I want to prove that this guy is maximal commutative, it is sufficient to prove that its classical limit, the subalgebra in the universal enveloping of U of GL2 of T, generated by the leading terms of this and this, is maximal commutative, but the subalgebra generated by leading terms of this and this here is just the subalgebra generated by E11 times TR and E22 times TR for all R. Okay. And this is obviously maximal commutative. Okay. So now let me describe the parameter space for commutative subalgebras in the Yangian. So first I note that the subalgebra doesn't change if we delay the parameter. So the actual space of parameter should be something like projectivization of the space of matrices.
There was a question. Why is it sufficient to check the leading terms?
Why
is it sufficient to check the? There was a question why it is sufficient to check the leading terms to prove that the subalgebra is maximal commutative. Sorry, let me.
Because if we had something commuting with everything in the subalgebra, then in the classical limit, the leading term of this something commutes with everything in the classical limit of the subalgebra. So the classical limit of the commutative subalgebra should be not maximal. Right? So it is sufficient. Okay, so I can assume that C belongs to this. But this is not the full truth, because so indeed we have a family of subalgebras depending on a point in this space. We still can define the algebra B of C by the same formula, but this won't be a flat family of subalgebras. Is not flat family of subalgebras. What I mean here, for generic C, the subalgebra B of C is generated by the coefficients of quantum determinant, which are always the same, D1, D2, D3, and so on. And the coefficients of the trace, tau 1 of C, tau 2 of C, tau 3 of C, and so on. The elements of so I have two generators of degree 1, 2 generators of degree 2, 2 generators of degree 3, and so on. And in fact, for generic C, in fact, for C, for all C different from the unity, all these guys are algebraically independent. But if my matrix C is 1, then the following happens. I have for C equals 1, I have D1 equals T11 plus T22, and tau 1 is the same thing. So these guys are dependent. This means that for C equals 1, this subalgebra becomes smaller than for generic C. So the family is not flat. On the other hand, I can still consider the limit of such subalgebra, limit of B of C, when C approaches 1, and consider the limit of the subalgebra B of C as a point in the Grassmannian, as the limit of subspace. This is well defined because, so on the one hand, the Yangian and the subalgebra B of C in the Yangian are both infinite dimensional spaces. On the other hand, the Yangian is filtered by finite dimensional subspaces. So I can regard this limit as the as the collection of limits of subspaces in the corresponding Grassmannians in the finite dimensional subspaces corresponding to filtered components. So this is well defined, and taking such limit, I automatically get a subalgebra of the same size as B of C. So taking the limit when C goes to 1 is a procedure that gives an algebra containing B of 1 and something additional. And this additional actually depends on how we approach the unity, from which direction. And it is easy to see. So if we consider C, for example, being 1 plus epsilon times chi plus O epsilon, and epsilon goes to 0, then what I get in the limit will be this b of 1 plus one additional generator, which is trace of chi times the matrix T11, 1, T1, 2, 1, T2, 1, 1, T2. So I mean that all these generators for C equals 1 will be algebraically independent, and depending on the direction I approach the unity point, I will get some additional generator of this form. Just any linear combination of Cij1. Okay, so this means that the true parameter space for commutative subalgebras in the Yangian of GL2 is the blow up of, so let me write this down, is the blow up of the projective space. So the true parameter space for B of C is blow up of the unity point in the projectivization of 2x2 matrices. So it is P3 blown up at one point. Okay, so so this is the example, and in fact, our result is
sorry, why?
at least
Why is it P3?
P3 blow up of P3 at one point.
So why 3? I'm confused.
Because 2x2 matrices is a 4-dimensional space.
Okay, yeah, sorry. Okay. Yeah.
So this is P3, and I blow up one point.
Yeah, sorry.
So our goal is to generalize this to Yangian of any type. To Yangian of G, where G is any simple Lie algebra. Okay, so because of the lack of time, let me just just formulate the result. But for this, I have at least I have to define this Yangian, or at least to say what it is. So the Yangian of G is a Hopf algebra of algebra, which can be regarded in two possible ways. First, as a deformation of the universal enveloping of G of T, and on the other hand, it is a deformation of the functions on the Poisson group, the congruent subgroup in the formal current group, right? So, and both of them are deformations of the Poisson algebra, just symmetric algebra of G of T. So we have actually this time. Yeah. So in fact, it is very useful to regard the Yangian of G in both of these ways simultaneously. So I mean that regarding the Yangian as the deformation of this algebra gives Greenfield's mu realization with generators deforming the Chevalier generators of G times the powers of T. EI times TR, FI times TR, and so on, and HI times TR. And from this perspective, we get RTT realization, which also goes back to Greenfield. But in fact, I learned about this realization from a recent paper of Curtis Wendland, where he studied this realization in detail. Namely, the ideology is as follows. So we can consider the following generators of this coordinate ring, namely to any representation. So let V rho homomorphism from G to GLB be a representation of G, of a group G, then I can consider the following functions on this congruent subgroup. So for any functional on V and for any vector in V, I can consider the matrix element of the group in this representation, namely delta beta V of T being just beta on G of T applied to V, right? So this is some power series in T. So this delta beta V of T is, well, it is the product of beta and V plus sum over all R delta beta V R times T2 minus R. And these are some elements from this coordinate ring. The RDT approach to the Yangian actually deforms and writes some defining relations on generators of this sort. Namely, I can write RTD generators of the Yangian as follows. So let V be any representation of the Yangian. So to do this, I need to know at least one non-trivial representation of the Yangian. Then I can take the value and consider T of U as the image of the universal R matrix. So let rho be the homomorphism from Yangian to and V over tensor 1 of the R matrix R of U. This is an element from the endomorphisms of V tensor the Yangian depending on U. For the Yangian of GLN, in particular for Yangian of GL2, which I already considered, we recover the T matrix, the generator. But the definition is general once you have the universal matrix and known in some representation of the Yangian.
Sorry, but I mean, surely you can define this TFU, but RTT wouldn't be the only relation if
RTT is not the only relation. You're right. So in particular, if you start from SL2, then you get Yangian of GL2.
Yeah, that's right. But in other types, you also need some symmetry.
The theorem proved by Wendland is the following: you can define the Yangian by RTT relations. You can define some algebra by imposing the quadratic RTT relations. Then it will be an algebra containing some center. And if you mod out this center, you get the Yangian of the corresponding simple layers. This is the same. And moreover, there is some explicit way to mod out this center.
Thanks.
Okay, so right. So once you have this realization, you can define for any group element.
Good. So there are two questions from two different people. One is, can you do E8 the same way?
Yeah.
And another question is, can you do this for quantum affine rather than for Yangian?
For
quantum affine algebra, you could do, you could still do RTT defined exactly in the way you said. It's just applying representation, fundamental representation to.
Yeah, you're right. In fact, I didn't think a lot of about
because
this.
somehow
Probably.
No.
So at least you get some. Yeah. So by considering this guy and opposing RTT relation, you get some algebra which surjects onto quantum affine, but I'm not sure if the kernel is generated by some central elements, as in this case. Probably this is true. Probably not. I'm not sure.
But in Yangian, you know, you can use RTT relations if you just vary over. If you just not use the first fundamental, but you vary over possible representations, then you can, like, all these conditions together. Of course, all these RTT relations from different pairs of representations, of course, define give you all relations on the Yangian. Somehow, this Curtis's theorem just tells you that you don't need to go to these depths. You can just take the first fundamental and mod out by the center, right? Okay.
Yeah. So now if you to any element of the group, you can assign a commutative subalgebra generated by trace rho of C times T of U trace over P for all finite dimensional V. So this is not very explicit definition, of course, because it involves all finite dimensional representation, but it is something. So one can prove that, of course, this subalgebra is always commutative, and moreover, to generate this subalgebra, you actually need only finitely many representation, in fact, only fundamental representations. Fundamental. So, for example, if your algebra G is SLN, then you just need the evaluation representation Cn, the evaluation representation lambda 2 of Cn, and so on, lambda n minus 1 of C. So you just get n minus 1 series of generators. Okay. So okay. So now our theorem. This construction gives you a family of commutative subalgebras parameterized by the group G, and you can assume that G is a joint group. but this G is still non-compact, and for general G, there is no obvious analog of the space of matrices to embed it into. Okay, so so the compactifying this space is a problem, and our main theorem is that this family of subalgebras extends to the Concini Procesi closure of G. So the family E of C extends to closure of G, which can be defined as follows.
Before you raise the proposition, can I ask one thing? So the proposition in the very bottom that says that that you can take the first fundamental representation. So if you want to define Yangian for GLN, you can take the first fundamental representation and then mod out by center generated by these n representations.
Right.
But isn't it enough to just define the quotient out by q that equals 1?
Right. Yeah. So if you are generating the Yangian from just the first fundamental representation, right? You get the Yangian of GLN, and to get Yangian of SLN, you have to mod out the quantum determinant.
And if you mod out, and if you also use the other fundamentals, what do you get?
Yeah. So the center will be bigger.
Yeah.
So if you take as the generating representation, for example, the sum of all these guys, then the algebra you get will contain the center of the size generated by infinitely many generators corresponding to this, corresponding to this, corresponding to this, and so on. So to any summand, it will correspond a series of central generators. Right. So the Concini Procesi closure is the following. So you can embed the group into projectivization of endomorphism space of any representation with the generic highest weight. So let lambda be regular highest weight, and take the closure of this group in this projective space. This is a very this is actually a very nice closure. It is smooth G times G variety whose G times G orbits with finitely many G times G orbits, namely with orbits corresponding to subsets, those subsets in the set of simple roots of G, and all these orbits can be explicitly described. So our theorem is that we get precisely this closure of the group, and one can describe explicitly the subalgebras corresponding to boundary points of this closure, at least to corresponding to generic boundary points of this closure. So in general, these limiting subalgebras are going to be, again, beta subalgebras, but in smaller Yangian inside the Yangian of G. So the Yangian of G contains Yangian of any Levi subalgebra in G, and it contains its own beta subalgebra, and all such beta subalgebra in the Yangian of Levi arise in this way. So the most degenerate one is just the Cartan subalgebra of the Yangian, corresponding to Levi being the Cartan. Okay, so maybe I have to stop at this point because the time is up. Sorry for.
Okay, well, thank you very much. Thank you, Leonid. And if you have any questions, please go ahead. Okay, maybe, well, I have a couple of questions. So, well, you described this commutative subalgebra, so you probably have some quantum integrable systems in mind that.
So thank you for this question. So for me, the motivation for doing doing all this is comes from XXX integrable system. On the one hand, XXX spin chain, because the elements of beta subalgebras acting in the tensor product of evaluation representation of the Yangian are the integrals of the XXX Heisenberg chain. On the other hand, the same operators, the integrals of this spin chain, arise as operators of quantum multiplication by the cohomology classes on quiver variety corresponding to G. So that's why it is interesting to solve spectral problem for this subalgebra in a representation of the Yangian. And so our idea is to analyze this spectral problem in the following way. So we can regard the spectrum of beta subalgebra in a representation as some covering of the parameter space, of this compactification of parameter space. So this gives some natural way to assign to the spectrum of beta subalgebra in a representation some combinatorial datum, because you can get the Cartan subalgebra in the Yangian as a limit point of beta subalgebras, and the spectrum of the Cartan subalgebra in a relatively simple representation is known, and it is something combinatorial. On the other hand, the spectrum of generic B of C is something complicated, and to describe this spectrum, we have to solve Bethe ansatz equations, and they cannot be solved in general. But the describing of this parameter space gives you some way to at least to write some to write explicitly some elements of Galois group of the Bethe ansatz equations. Namely, you can realize Galois group elements as monodromy of this covering along some paths in the parameter space. This is well, this is some part of our plan for the future regarding this problem. On the other hand, in more degenerate situation, not XXX spin chain, but it's degeneration Godin chain. This monodromy of Bethe ansatz problem was studied in our joint work with Joel Kamnitzer, Alex Weeks, and Eva Halacheva. And we relate this monodromy Galois group action to some natural combinatorial bijection by bijection on Kashiwara crystals coming from cactus group action by commuters. So we hope we have something similar here with Kirillov-Reshetikhin crystals instead of usual Kashiwara crystal. And some maybe unknown get generalization of cactus group acting on Kirillov-Reshetikhin crystals. So we expect this.
Thank you. Okay. Any other questions? Okay. Well, if there are no questions, then let's thank Leonid again. And next time.
Thank you very much.
And next time we'll have Misha Bechstein speaking. Okay. And let me end the recording.